Okay, so hopefully I can do this in one take. I'm doing it in person for this week during Soyuma's office hours. It's only one person watching. Hi, one person. He waves back. Uh, so y'all wanted pretty much everything that was on the list of the form that I sent out on Tuesday. So this should cover pretty much all of it. It doesn't do signed printing out a signed number because at least for factorial, you don't get a negative number, so I didn't need to implement that. But there's sort of two parts to this recitation. There's the register spill part, and then there's the arithmetic part, which uses repeated division to print out a ASCII number, and then it sort of just repeatedly divides by 10 and shifts out a digit. It's really cool. You'll see. You can download the code at the second link and fill it in as I go through it, but I'll be going pretty fast. So if you're, well, unless you're the one person here, you are watching after I record, so you can just pause and ponder and make sure you understand what I'm typing. Okay, so algorithm, the algorithm we're doing today is factorial, again, like last week, except this one is in pure assembly. I'm using SPIM for the simulator, so there's a few instructions that you guys don't have in Zybooks if you're in the class, which is the move instruction and load immediate, etc., etc. It's a pretty simple algorithm. It just multiplies, well, you know, factorials. I don't even have to explain it. But in this case, it prints out the result in ASCII digits or Unicode. Well, they're the same thing. ASCII and Unicode are the same for the lower 128. So this is what we're making. You'll notice that there's a recursive call here that calls itself usually. It's called factorial. If you watched last week's video, you'll understand how specifically this assembly works, but I'll be filling it in. And then there's the print decimal function, which prints a new line along with the base 10 representation of the factorial number. All right. So let's start with the first one, the register spill.mips file. For this one, I won't be filling in the print decimal function. I'll just be filling in the factorial function. The main section of this function just calls factorial of 5, and I can change this if I want, and then it'll move the result into the argument register and then print it out. It's pretty simple. And that'll just call this whole thing. But let's just start filling this in. Right. So for any recursive function, you absolutely have to have a base case, or otherwise it will just call forever, and you'll have a stack overflow, which is always fun. So there's, I think, three places where we need to add code here. So this is the base case, right? And the base case for a factorial function is where the input number is a 1. So factorial of 1 is 1. You don't need to do a recursive call there. So we just basically return 1. Right. So what we need to do is we need to write a conditional statement that checks if we are in the base case, and then we'll run the subsequent code, and if not, we will skip over it. Right. In assembly, if statements are sort of just reversed, so we want to check that it's not equal to 1, and then we will jump over the conditional code. Right. So branch if not equal to $sign v0, the argument, and I'm going to use t0 for a temporary register, and I'm going to factorial base case skip. Right. So let me move into load immediate t0 1. Right. So we're going to compare the argument to 1, and if they're not equal, aka the argument isn't 1, we're going to skip over the factorial base case here, and I'm going to remove the no ops so that y'all don't get confused. All right, cool. So that's the base case taken care of. And now we need the recursive case, right? So in MIPS, we have these, the return address and the arguments and return values in registers. So to avoid losing that data, which we will need to, return out of the function without jumping to some random portion of the code, we'll need to push it onto the stack, right? And we need to do the stack instead of static memory because each subsequent recursive call will need to have essentially like new instances of those variables, which are store the registers, right? If we just had one static variable for the factorial call to store registers into, each subsequent recursive call will just overwrite that data and it'll corrupt it, right? So there's 3 registers that we need to store. Wait, 3? No, 2 registers that we need to store. We need to store the argument and the return address, right? So we need to allocate enough data on the stack to hold those two variables. So that's 8 bytes. So add I to the stack pointer, and then -8. And there's no sub I. You just have to use add I with a negative value, right? And then we're going to store a word. And then we're going to store first the return address into the second half of that space we've just allocated. Right, so now 4 bytes. And then we're going to do the same thing here, store word, not return address, argument 0, and into 0 offset stack pointer. Right? So what these 3 lines I did here is allocated space for 2 words on the stack, right? Store the return address with an offset of 4 and the argument with an offset of 0 on the stack, right? So each subsequent call will allocate another 8 bytes on the stack to store these values before it makes the recursive call. Right, cool. And then this is the recursive call, right? Conveniently, we can just use the argument register to get the new argument for the recursive call, because the original value, say 4, is in here, so we need to do a recursive call for factorial 3. So we just subtract 1, and then we jump and link factorial, and then we move the return value from that recursive call into a temporary address, because we will need both the original argument and the recursive return value to calculate the multiplication down here. Right, so now we're going to pop back off the values from the stack, and very conveniently I can just copy paste most of this code. How do I select? There we go. Right, so I can just, instead of doing a store word, I just load the word. Right, and then I can reset the stack to its original point. So we deallocate those 8 bytes of data, right? And then what the function will do is it will multiply the return value of the recursive call, which got stored in T0 here using this move pseudo instruction, and the original argument, which we just popped back off the stack, and store that into the return value register, right? And then it'll return from that. Okay, cool. So if I run Shift Control B, I get an error. Where is that? That's incorrect. What's going on here? Okay, I have... Okay, this base case here is incorrect because this is looping incorrectly. The stack should not be this big for such a simple program. Right, so if I look at this, that's the return. Yeah, see, I did that wrong. It's supposed to be A0, argument 0, not the return value 0, right? So then I run it. Yeah, okay, then it works. Great. So that's factorial 5, and I can test this with some other number, 12. The 32-bit word size kind of limits what you can do with factorial very quickly. All right, cool. That's factorial 12. Okay, now for the second part. This one's a little more complicated. I have the factorial code filled in here, and you'll notice that I have this whole thing set up correctly this time without the whole shenanigans of me messing up. But then print decimal is not filled in. Now this is kind of a more complicated function. It's got a bit of code, but it's a rather simple process. All it does is it takes in some sort of, well, in this case, positive integer as a value, and if you want to do signed, you'll have to check for the sign bit manually, and then complement it, and then do all that stuff so that you can use division properly. But what all of this does is it pushes a single character onto the stack and then prints directly off of the stack, right? And it pushes an ASCII character onto the stack, right? So it'll repeatedly take the number, right, the argument number, store it in this register here, and divide it by 10 over and over again. And it'll take the remainder of that division and store that as a character on the stack, right? So 15 divided by 10 is 1 remainder 5. It'll push the ASCII character for 5 on the stack, and then 1 divided by 10 is 0 remainder 1. It'll push 1 onto the stack, and then it's 0, so it doesn't push another character on the stack, and we'll just do the syscall to print off the stack pointer. Okay, so let's go through this a little more detailed. The first line here for the function call is to store the stack pointer into a register, right? And this is pretty important because as we're pushing multiple bytes onto the stack, it's kind of a little more difficult to like restore the stack to its original state. So I'm just going to take the stack pointer, which is some number, some really, really large arbitrary number that points to a memory address, and store that in S0, and then at the bottom I'll restore it, right? Okay, cool. Now what we're doing right here is we're pushing a null byte. So the print system call, the thing in the SPIM emulator that will look at a memory address and print something out, it will stop at a null byte, and a null byte is 8 zeros in a row, right? So what I'm doing here is I'm allocating 1 byte on the stack, right, and then I'm moving into a temporary register the value of 0, and then I'm storing a byte, a single byte, 8 ones and zeros onto the stack. So what I've done here is that at the lowest point on the stack, which is the top of the stack, I've stored 8 zeros, right? And then that will be used to tell the print system call to stop printing stuff out, so it won't print out whatever garbage is on the stack after this, right? Okay, cool. And then what we're going to do is we're going to push a line ending to the stack as well. So it's not just enough to push the null byte, it needs to have a line ending as well, right? So if you want to print something out in code, you have to usually specify if you have a new line at the end of whatever you just printed out. Otherwise, it'll just print things out one after another, and it'll be really, really ugly. So in this case, a line ending, an LF line ending, is 0x0a. So number 10 hex A for ASCII, right? Cool. So that'll do the same process for the null byte, but it'll push the line format to the stack, right? And if you remember, the stack pointer decreases as you add more to the stack. So looking from basically reading from left to right, we'll have the numbers and then the line ending and then the null byte in order, right? So because the stack grows downwards in the negative direction, it'll be in order when we add stuff to the stack. Okay, cool. Now what we need to do is we need to make a loop where some register does not equal 0, right? In the example I gave where we did 15, shifted out 5, and shifted out 1, we stopped when the quotient of the division of 1 was 0, right? So we want to check if the quotient we have is 0, right? It's kind of a tough sentence to say, but in this case, the quotient will be stored in S1, right? So we take in the argument integer, right, and we copy that to S1, right? So S1, so BQ $S1. So if S1 is equal to 0, we then move to print decimal, push number exit, right? This label here. Cool. And then the no op I shall remove, because that's confusing for y'all. Okay, cool. So then what we're doing is we're storing 10 into a temporary register. So I know, but from intuition, this would tell me that T0 is the thing we're going to be dividing by. So we're dividing S1 by T0, and then we're going to get a quotient and remainder, right? Okay, so let's look at these 3 comments here, these 3 places where you have to add code. So it says the quotient stored in low and remainder stored in high, and you access these registers using specific commands, right? So this is going to be our division operation here, right? So I'll look at the division instruction using my snippets. Divide high to low. So we're going to divide S1 by T0, right? And then the quotient of that will be stored in the low register, and the remainder will be stored in high, right? Okay, cool. Now, after that, after we've done the division operation, we need to push the remainder to the stack, right, as an ASCII character, right? So, say the input number was 15, we divide by 10, we get a quotient of 1 and a remainder of 5. We change that binary number 5 into an ASCII character somehow, and then we push that to the stack, right? So what we're going to do is we're going to remainder, MFHI. We want to get from the high, and we're going to put that into T0, right? And we're going to add immediate T0, 0, and 0x30. So ASCII characters define the base 10 number system starting at 0x30. So a number 5 would be 0x35, and a number 8 would be 0x38, and so on and so forth. So we just add the 0x30 to that binary number, and we end up with a nice clean ASCII character for each number. It's a really, really nice shorthand. And then we need to store that onto the stack. All right, so I'm just going to copy this code here, all the way up here, where we put a number onto the stack. All right, allocate another byte on the stack pointer. We already have T0 set up, so we can remove this, and we're going to store a byte of T0 into wherever the stack pointer is. All right, cool. Now that we've pushed the character, we need to add in code to repeat the process with the quotient, right? So that example 15, it's not good enough to just do it once and push out 5. We also need to push out the 1. So the quotient we have, we need to put back into the original register that we use, which is S1. S1 stores the thing that we need to divide by. So if we MFLO into S1, that will store the quotient into the register that we then keep dividing by 10. And so the process will repeat for every single digit. Right, and I'm going to jump branch back up to print decimal, push number. Right, cool. And then when it exits, it'll print out, and we're using the print system call, and then it will restore the stack pointer to this value that we stored in S0, and then it'll return from that. Right, cool. Let's try this. Hey, it worked first try. No error. All right, cool.